Picture a desert horizon. Egypt, the heat-blurred sky above Dahshur. 46 centuries ago, the sand stretches flat and white in every direction. The way it has stretched since long before any human being thought to interrupt it. And then, breaking the line of that horizon like something impossible, a pyramid rises. But this one is different. Look at it carefully. Right there, halfway up, the angle changes. At 147 feet above the desert floor, the sides of the pyramid suddenly lean inward, shift to a shallower slope, and the thing that should be a geometric absolute becomes something else. Something irregular. Something that looks, even to an untrained eye, like a pyramid that changed its mind. It bends. And in the 4,600 years since it was built, that bend provoked the same response in almost every person who has ever seen it. What happened? Not what kind of rock. Not what tools were used. Not even who built it. What happened? Because the bend is not supposed to be there. Pyramids are supposed to be perfect. Their entire meaning depends on perfection. The smooth sides, the geometric precision, the unswerving angle from base to apex. These are not aesthetic choices. They are theological ones. The pyramid represents the eternal, the unchanging, the absolute. A pyramid that bends is a contradiction in terms. And yet here it stands, right here in the sand south of Memphis, in the necropolis of Dahshur, the bent pyramid of Sneferu, the only pyramid on earth whose exterior tells the story of a crisis that almost swallowed it whole. What you're about to hear is not myth. It's not legend. It's not the embellishment of civilization trying to explain away a mistake. It's a documented account of an engineering emergency that unfolded inside a half-built pyramid in real time 4,500 years ago. A crisis so severe that the builders had to make a decision no pyramid builder had ever been forced to make before. Change the design, mid-construction, in stone, or lose everything. This is the story of how they did it, and why the fact that they did it may matter more to the history of human civilization than the pyramid itself. To understand what broke, you have to first understand what was being built. And to understand what was being built, you have to step back from the stone entirely and enter the world that made it, the 26th century before the Common Era. Ancient Egypt is not ancient yet. That designation, ancient, distant, lost, would not arrive for thousands of years. In this moment, Egypt is alive, thriving. The Nile floods on schedule, just as it has for generations, and just as it will for generations to come. The harvests are good. The granaries are full. The administrative machinery of the Egyptian state is operating with precision that most modern institutions would find difficult to match. This is the Old Kingdom. Historians would eventually give it that name because it would need to be distinguished from what came before and what came after. But to the people living inside it, it is simply Egypt, the most organized, the most prosperous, the most extraordinary civilization on earth. And at the center of all of it sits a man named Sneferu. His name, in the ancient Egyptian language, means something close to make beautiful. And from the moment he took the double crown of Upper and Lower Egypt, Sneferu appears to have absorbed that meaning completely. He is not a pharaoh who rules from stillness. He campaigns into Nubia, pushing the southern borders. He dispatches fleets to the coast of Lebanon to return with cedar that Egypt cannot grow. He opens turquoise mines in the Sinai Peninsula. He builds. He moves. He reaches. He is, by every measure available to modern historians, a man of extraordinary energy and appetite. But here is the thing history will remember him for. The thing that outlasted his campaigns, his fleets, his mines, and his fame. He built pyramids. Not one, not two, 3 of them, possibly 4. And the sheer volume of stone he moved during his reign, the raw tonnage of rock lifted from quarry to desert sky, exceeds what his son Khufu would later move to build the Great Pyramid of Giza. Sit with that for a moment. The man who came before the most famous building in human history built more. Not a more famous monument. More stone. More volume. More ambition poured into the desert floor. Sneferu moved more rock in a single reign than almost any builder in the entirety of the ancient world. Why? What drives a man, even a pharaoh, to that scale of obsession? The answer lies not in vanity. It lies in cosmology. For the Egyptians of the Old Kingdom, a pyramid was not a tomb, Or rather, it was a tomb the way a cathedral is a room with a roof. Technically accurate and completely insufficient. A pyramid was a machine for transformation, a mechanism for the passage of the divine from one state of existence to another. Its shape was not arbitrary. It was precise, intentional, spiritually loaded at every angle. The Egyptians called a sacred stone at the top of an obelisk, and later at the apex of a pyramid, the benben. It was the original hillock, the primordial mound that rose above the waters of chaos at the beginning of creation when the god Adam first appeared. The pyramid slope was meant to echo the slant of the sun's rays as they broke through clouds in the morning. What Egyptians call the sun's beams made visible and solid. The rays of Ra, cut in stone, fixed in place, angled just so to guide the soul of the departed king upward, into the sky, into the company of the gods. This was not poetry. It was architecture. It was engineering with a divine brief. The angle mattered. The perfection mattered. Any deviation, any roughness, any compromise in the geometry was not merely an aesthetic failure. It was a theological one. The king was not simply a man who wore a crown. He was the pivot point between two worlds. He managed a relationship between the living and the divine. He held the world in its right order, what the Egyptians called Mat, and when he died, he had to make the crossing into eternity with maximum dignity, maximum surety, maximum cosmic support. The pyramid was that support, made permanent, made stone. So when Sneferu began building, he was not doing construction projects. He was fulfilling a covenant, an obligation so vast and so sacred that no amount of labor, no amount of stone, no amount of risk could be considered too much in its service. He inherited this obligation at a very specific and very consequential moment in its evolution. 2 generations before Sneferu came to power, a man named Imhotep, architect, physician, and eventually a god, had built the step pyramid of Djoser at Saqqara. Nothing like it had ever existed on Earth before. What had previously been a mastaba, a low, flat, bench-like tomb of mud brick, Imhotep transformed into a monument of 6 ascending stages, stacked in limestone, rising roughly 200 feet into the Egyptian sky. The world was never the same after it, but the step pyramid, for all its shattering brilliance, was still an intermediate form. It was a staircase to heaven, and that was exactly what it was meant to be. But in the years between Djoser and Sneferu, Egyptian theology was moving, refining. The true pyramid, smooth-sided, uninterrupted, geometrically absolute, was becoming the new ideal. No more visible steps. No more stages. Just pure angle, pure ascent. The rays of Ra solidified perfectly. Sneferu wanted to build the first true pyramid, a smooth-sided monument that would define his reign and his place in the divine order forever. He began at Midam. The site sits roughly 60 miles south of modern Cairo, in the desert beyond the Fayum oasis. The pyramid that rises there today is not what was originally built. What you see is a remnant, a strange, tower-like core of stone surrounded by massive apron debris that has accumulated over millennia. It looks damaged because it is damaged, and the story of that damage is inextricably tied to everything that happened later at Dahshur. But before we follow that thread, there is something that must be said about who actually built these monuments. Because the story of pyramid construction has been buried under one of the most persistent myths in all of popular history. The image of slaves, thousands of broken men, driven under the lash by brutal overseers, die in the sand beneath impossible blocks of stone. This image was largely invented by historians who visited Egypt 2,000 years after these pyramids were built. Herodotus, the Greek historian who recorded it most influentially, was a brilliant observer and a gifted storyteller. He was also working from memory, from rumor, from interviews conducted across a language barrier about events that had occurred centuries before his grandparents were born. The reality that archaeology has uncovered is different, profoundly different. The workers who built Sneferu's pyramids were Egyptian citizens. They came from villages across the kingdom, rotating in organized shifts, serving what appears to have been a form of national labor conscription, likely tied to the agricultural off-season, when the Nile floods made farming impossible and the workforce had to be redirected somewhere. They were housed in permanent worker villages. They were fed with unusual generosity, meat, bread, fish, and beer in quantities that exceeded the typical Egyptian diet. Their injuries were treated. Their bones, recovered from worker cemeteries near Giza, show heel fractures, evidence that someone set broken bones, that someone administered care, that the laborers who fell on a construction site were picked up, not left behind. This was not a kingdom built on cruelty. It was built on organization. And organization, at the scale required to move millions of tons of stone, is itself one of the most astonishing achievements in the entire history of our species. Sneferu's builders were not merely laborers. They were participants in a precision machine of knowledge, craft, and cultural meaning. The overseers understood geometry. The quarry workers understood stone in the way that surgeons understand the body, intimately, experientially, through generations of accumulated knowledge that existed nowhere in writing. The engineers, we have almost none of their names, almost none of their words, were solving problems of weight and angle and pressure and foundation that the world would not see again until medieval Europe began building cathedrals. And those problems were about to announce themselves, loudly, permanently, because building a pyramid is not like building anything else. A pyramid is not just heavy. It is the shape of accumulating heaviness. Every stone laid above adds to the pressure on the stones below. Every layer built increases the load on the foundation. And as the structure rises and the angle of its sides concentrates that weight toward the center, the forces inside the stone multiply in ways that are not always visible, not always predictable, and not always survivable. At Mitam, Sneferu's builders were about to encounter this reality for the first time. What happened there? What collapsed? What cracked? What failed? And what the builders carried away from that failure into the desert at Dahshur would determine everything. Every angle, every internal design, every desperate decision made in the middle of a construction crisis 147 feet above the desert floor. The ground at Mitam had something to say, and the builders who arrived at Dahshur would find that the ground there had something to say as well. The question was whether they would hear it in time. There's a pyramid in Egypt that most people have never heard of. It stands 60 miles south of Cairo, in the desert beyond the Fayum Oasis, and it looks like nothing else on earth. Not because it is beautiful, not because it is grand, but because it is broken in a way that makes you stop mid-thought and stare. What remains at Mitam today is a tower, a blunt, three-step core stone, roughly 200 feet tall, rising from a sea of rubble so vast and so deep that it covers the desert floor for hundreds of feet in every direction. The debris field is enormous. And when you stand at its edge and look inward toward that jagged central tower, you are looking at the remains of what was supposed to be one of the great monuments of the ancient world. The outer shell collapsed. The smooth casing, the beautiful, finished, geometrically perfect surface that would have made this a true pyramid, the first of its kind, is gone. It did not weather. It did not erode. It fell. And the question of exactly when it fell, and what the falling of it meant to the men who were trying to build an even larger pyramid 40 miles away at Dahshur, is one of the most quietly dramatic questions in all of Egyptology. Here is what we know. The structure at Mitam began as a step pyramid. 7 distinct stages, rising in the traditional form that Egyptian builders have been perfecting since the time of Djoser. Some historians believe it was started by Huni, the pharaoh who ruled immediately before Sneferu. Others, looking at the same inscriptions, the same graffiti, the same fragments of evidence, believe Sneferu built the whole thing himself, beginning to end. The attribution is genuinely uncertain. What is not uncertain is that Sneferu's name is found there. His presence is in the stone. What is also not uncertain is what happened to the structure next. At some point, the timeline is debated. The reasons are argued over, but the physical evidence is not. The step pyramid at Mitam was converted. The existing stages were filled in with carefully cut limestone packing. The steps smoothed over, the angle unified, and a white Tyrol limestone casing was applied to the outside surface. The result, if you could have stood in the desert at Mitam and looked at it in that moment of completion, would have been breathtaking. A true pyramid, smooth-sided, geometrically exact. The first, the dream-made stone. And then something happened. The outer casing came off. Not slowly, not partially. The debris field at the base of Mitam is a geological record of a catastrophic structural failure. Millions of cubic feet of stone, the entire smooth exterior of the monument, separated from the core and cascaded outward in all directions. What was left was a raw inner structure, the step core that had always been there beneath the casing, exposed, stripped, and standing alone like a skeleton after the flesh has fallen away. Now, here is where history gets complicated, and complicated history in this case is far more interesting than a clean story. For most of the 20th century, archaeologists assumed the Mitam casing collapsed during the Old Kingdom, during Sneferu's own lifetime, perhaps even during construction of the bent pyramid. The argument was elegant and logical. The failure at Mitam caused a panic at Dahshur. Sneferu's engineers saw their first true pyramid destroy itself, rushed to Dahshur where a second pyramid was already rising, and made the desperate decision to change its angle mid-construction to avoid the same fate. The two crises were linked. One caused the other. It is a satisfying story. It connects two monuments the way a good documentary should. And it may even be true. But here is the complication. Visitors came to Mitam in the New Kingdom, 1,000 years after Sneferu's reign. They left graffiti inside the pyramid's passages, carved into the walls in a casual, slightly boastful manner of ancient tourists everywhere. And those graffiti speak of a beautiful pyramid, a monument worth making the journey to see, a structure that inspired them. If Mitam had already collapsed into the ruin we see today, these visitors would not have described it that way. They would have described rubble, which means that for 1,000 years after Sneferu, the Mitam pyramid may still have been standing, casing intact, angle preserved, the first true pyramid, holding its shape across 10 centuries before the final structural failure came. This does not mean the construction of Mitam was smooth. It does not mean Sneferu's engineers learned nothing from the work there. It means the relationship between Mitam and Dahshur is more subtle, more complex, and ultimately more interesting than a simple chain of cause and effect. What Mitam taught, even in the process of being built, was a lesson about casing. The outer limestone applied at Mitam was laid in a way that modern structural engineers would look at and recognize immediately as precarious. The bed joints, the horizontal surfaces on which each course of casing stone rested, sloped very slightly outward, not dramatically, just enough to mean that the weight of each stone, rather than pressing inward and down into a stable interlocked mass, had a persistent, quiet tendency to press outward and away from the core structure. And the foundation beneath the casing at certain points was not bedrock. It was rubble fill. Compacted, yes. Smooth, yes. But not bedrock, not the unmoving certainty that a structure of this mass demands. The casing at Mitam was resting on ground that, given enough time and enough load, would allow it to drift, slowly, invisibly, until it did not drift anymore, until it fell. This is the mechanism behind the debris field. Not a dramatic earthquake, not a sudden catastrophic event from outside, a quiet, incremental failure that the structure had been building towards since the last stone was placed, a structural inevitability that may have taken anywhere from decades to centuries to finally express itself. Now bring that knowledge to Dahshur. Bring it to the men standing at the foot of a new pyramid, looking up at a structure that is already, by the time the crisis begins, far larger than Mitam, a structure whose angle is 54 degrees, steeper, heavier, concentrating far more weight onto its foundation than anything previously attempted. A structure whose foundation is not the reassuring solidity of bedrock, but something softer. Something the builders chose without fully understanding what was beneath it. The question that should already be forming in your mind is this. If the Egyptians knew, even partially, even intuitively, that foundation mattered, that angle mattered, that the way a casing stone was laid could determine whether a monument stood for eternity or fell into rubble, why did they begin the bent pyramid in the way they did? Why the aggressive angle? Why Dahshur at all? The answer requires you to understand something about the pace of ancient engineering knowledge. It did not move the way modern scientific knowledge moves. There were no journals, no conferences, no formalized system of recording structural failure and circulating the lessons to the next project's chief engineer. Knowledge lived in people. It passed from master to apprentice, from overseer to overseer, shaped by what each generation of builders had personally experienced and personally survived. What Mitam was teaching was not yet fully understood, because Mitam had not yet fully failed. And what the ground at Dahshur was hiding, The unstable, clay-rich shell that lay beneath a deceptively solid-looking surface layer was not yet visible to any eye or any instrument. The crisis was already building, silently, underground, at the molecular level of foundation that was slowly, imperceptibly, responding to the weight being stacked on top of it. All the ambition, all the theology, all the organizational genius of the Egyptian state, the thousands of workers, the overseers and engineers and quarry masters, the entire vast machine of Sneferu's construction program, all of it resting on ground that was beginning to move. No one knew it yet. The pyramid was rising. The angle was steep. The stone was being cut and laid and dressed with precision that staggers the imagination even today. From a distance, from the edge of the plateau, from the vantage point of any overseer watching the structure climb toward the sky, everything looked exactly the way it was supposed to look, except for one thing. Something, somewhere deep inside the pyramid, was beginning to crack, and the men who first discovered it in the darkness of those interior chambers were about to understand what none of their predecessors at Mitam had been forced to understand in quite this way. That a pyramid in the process of building itself can also be in the process of destroying itself. At the same time, in the same stone, the question was no longer whether they were building the monument correctly. The question was whether they could save it at all. Dahshur, say the name, and it gives you nothing. No resonance, no mythology, no immediate image the way Giza does. Most people who know the pyramids of Egypt have never heard of Dahshur at all. And that obscurity, that quiet, overlooked quality, is part of what makes what happened here so remarkable, because this was not some secondary site, some afterthought in the geography of the old kingdom's ambition. This was a deliberate choice, a considered decision by men who understood their landscape with an intimacy that most modern people bring to almost nothing. Dahshur sits roughly 25 miles south of modern Cairo, on the western edge of the Nile Valley, where the fertile black soil of the floodplain gives way to the pale desert plateau. From certain angles, on certain days, you can stand at Dahshur and see the pyramids of Giza in the distance to the north, and the tower that remains of Mitam somewhere to south, and feel yourself at the center of something, a chain of intention, a line of monuments that stretches across the desert like a sentence written in stone. Sneferu's planners chose this site for reasons that were almost entirely rational, and that rationality makes what followed all the more devastating. The plateau here was wide enough to accommodate a base of royal ambition without running out of solid desert floor. The Nile was close enough to allow the transport of materials, limestone from the quarries at Tura, granite from Aswan, the constant supply of food and water and equipment that feeding a construction workforce required. The bedrock, or what appeared to be bedrock, was accessible near the surface. The horizon to the north was unobstructed, giving the pyramid a visual dominance over the landscape that suited its cosmic purpose. And there was another consideration, one that modern people rarely think about when they imagine these sites. A pyramid of Sneferu's scale required enormous lateral space around its base, not just for the monument itself, but for the ramps, the worker facilities, the stockpiles of cut stone, the administrative offices of the project overseers. Saqqara, the necropolis already occupied by Djoser's step pyramid complex, was beginning to fill. Dahshur offered room, empty, open, available room in a direction, south or along the plateau, that pointed away from the already crowded north. The choice made sense. All of it made sense. And so the work began. The base was laid out with the methodical precision that Egyptian engineering had been refining for generations. Surveyors stretched their cords across the desert floor, establishing right angles with a geometric certainty that modern measurements confirmed to within centimeters. The base of the bent pyramid, when staked out, was a square measuring approximately 188 meters on each side. If you were trying to feel the scale of that in your mind, set yourself at one corner of a square and walk to the next corner. It would take you almost 2 minutes at a comfortable pace. Now imagine doing that on all four sides. And then imagine stacking stone on that footprint until it touches the sky. That was the plan. And the angle was 54 degrees. This is where the decision requires understanding, because it was not arbitrary. 54 degrees was not some reckless gamble born of ignorance. It was a choice with precedent, a choice that followed logically from the step pyramid tradition, where the conversion of a step structure into a smooth-sided monument had naturally produced angles in that range. It was a choice that reflected a particular relationship between height and base, a ratio that the Egyptians understood as aesthetically and spiritually correct, that placed the apex at the right visual height relative to the foundation, that made the pyramid look like a pyramid should look. It was also a choice that, at this particular site, on this particular foundation, was going to cause the structure to tear itself apart from the inside. But not yet, not in the beginning. In the beginning, everything was glory. The quarry work that fed the bent pyramid's construction was operating on a scale that defies easy comprehension. Limestone from the Tura quarries across the Nile, the fine, white, dense limestone that would form the casing, arrived by barge along the Nile and then overland by sledge, hauled by teams of workers across the desert floor on tracks that were periodically wetted to reduce friction. The rougher local limestone that would form the body of the pyramid came from quarries closer to the site, and the logistics of managing both supply lines simultaneously, maintaining quality, quantity, and the rhythm of delivery that kept the construction moving, was itself an engineering problem of considerable sophistication. Wooden sledges, copper chisels, dolerite pounding stones that could shape granite, ramps of compacted rubble, sand, and mud brick that grew alongside the rising structure, allowing workers to haul blocks upward as the pyramid climbed. The ramp systems used at pyramid sites are still debated by engineers and archaeologists, a genuine open question about exactly how the stones reached their final positions at such heights. But the ramps existed. The evidence of them is in the ground. The compacted material, the pottery fragments, the tool marks on the stone. This was not mystical. It was not extraterrestrial. It was human ingenuity, human organization, and human labor, vast quantities of all three, deployed with relentless focus over years and years. Inside the rising structure, the builders were doing something that deserves particular attention, because it connects directly to the crisis that was coming. The bent pyramid was designed with two entrance corridors, an unusual feature that no pyramid before it had used. One entrance on the north face, one on the west face, each descending at a steep angle to the body of the pyramid before leveling out into internal chambers. Two separate corridors. Two separate access points. The reasons for this design are not definitively known. Some scholars believe it reflects the theological duality of Upper and Lower Egypt, the two crowns united in the person of the pharaoh. Others suggest the west corridor was added during construction for structural or practical reasons unrelated to theology. What is certain is that this double corridor design created two internal chambers inside the lower body of the pyramid, each one sealed away from the outside world by the accumulating mass of stone above it. And inside those chambers, the builders used a technique that was itself a significant achievement: the corbelled vault. A corbelled vault works by having each successive course of stone above an open space project slightly inward, past the course below it, until the two approaching sides meet in the middle. It creates a shape that looks like a tall, narrow inverted V, or like two stairways leaning toward each other until they touch. It is not a true arch. The keystone arch that Roman engineers would later perfect was not part of the Old Kingdom builder's toolkit. But the corbelled vault achieved something the arch would also achieve. It distributed the weight of the stone above the chamber outward and downward into the walls rather than concentrating it in a single crushing downward press onto the ceiling. The builders who designed the internal chambers of the bent pyramid were already thinking about load distribution, already thinking about the problem of putting a small, hollow, human-scale space inside an enormous, solid, stone-scale structure. Already thinking about how to make the void survive the weight of the mass surrounding it. They were already, in other words, engaged with the central engineering problem of pyramid building. They just did not yet know how much more urgently they were about to need that understanding. Because beneath their feet, beneath the carefully leveled foundation layer, beneath the first courses of the pyramid's massive base stones, beneath the planning and surveying and the geometry, the earth at Dahshur was not what it appeared to be. This is a part of the story that requires a different kind of attention, not the attention you give to human decisions, to strategy, to ambition and theology and engineering genius. The kind of attention you give to something that has no consciousness, no intention, no awareness of catastrophe it is quietly producing. The geology, the Nile Valley and its western plateau are not uniform. The desert floor that looks solid, that sounds solid when you walk across it, that can bear the weight of a human body without any visible distress. This surface conceals a substrate of layered sediments deposited over millions of years by the Nile's flooding cycle. Clay, silt, layers of fine alluvial material, compressed and recompressed by millions of years of inundation and drying, in a slow geological rhythm that has nothing whatsoever to do with the plans of pharaohs. At Dahshur, the plateau carries an additional complication. Beneath the relatively firm surface layer, the foundation in certain areas contains deposits of clay-rich shale. Shale, a sedimentary rock composed of compressed clay minerals, has a property that engineers today understand very well and test for very carefully before building anything significant on top of it. It deforms under sustained pressure, not dramatically, not immediately, not in a way that any visual inspection of the surface would reveal, but slowly, over time, under the kind of sustained, enormous, accumulating weight that a pyramid rising at 54 degrees imposes. Shale and clay-bearing materials will compress. They will shift. They will allow the foundation above them to settle. And settlement at the base of a pyramid does not express itself at the base alone. It propagates upward, into the stone, into the chambers, into the passages, into every place where two massive blocks of limestone are pressing against each other and relying on perfect stability beneath them to maintain the precise alignment that keeps the structure intact. The crack does not begin where the crack appears. It begins in the ground. It begins in the invisible, silent compression of a geological layer that was laid down millions of years before the first pharaoh drew breath. And it travels upward to the body of the pyramid in a process so slow, so incremental, that the workers laying stone at the summit would feel nothing, would see nothing, until the day they walked into the chambers below and looked at the walls, and saw what the walls were doing. There are cedar logs inside the bent pyramid, ancient cedar, imported from Lebanon at considerable cost and effort, cut and dressed and placed inside the internal passages and chambers as props, as supports, as structural bracing for walls that were not behaving the way walls are supposed to behave. These logs were not part of the original design. You do not plan to brace the walls of a pyramid with timber if you believe the pyramid is stable. You brace walls that are moving. You prop up passages that are closing. These logs are the fingerprints of fear. They're the evidence left behind by builders who descended into the heart of a rising pyramid and found something wrong, something the stone itself was telling them, in a language of cracks and displacements in walls that had shifted by fractions that, at the scale of a structure this massive, translated into structural emergencies. They saw it, and they understood what they were seeing, at least in part. This was not a small problem to be plastered over. This was not an imperfection that time would heal or that later layers of stone would conceal. This was the pyramid itself, the weight of it, the geometry of it, the aggressive angle of it, working against the ground it stood on, the stone above pressing down, the ground beneath yielding, and somewhere in the middle, in those chambers and passages where human beings had to walk and where the body of the king would eventually rest, the consequences of that pressure accumulating in the only form pressure ever takes when stone is involved. Cracks, displacement, the beginning of failure. The question that now arrived, the question that landed on whoever was responsible for this project with a force that must have felt almost as heavy as the pyramid itself, was not a simple one. It was not a question with an obvious answer or a gentle answer, or even a survivable answer in the conventional sense. The question was this: how do you stop a pyramid from destroying itself when the pyramid is already half built? Nobody in the history of Egypt had ever faced this question before. Nobody in the history of the world had ever faced this question before. And the men who now faced it at Dahshur, standing at the base of a half-risen monument with a cracking interior and a shifting foundation, and all the theological and political weight of Pharaoh's eternal fate resting in their calculations. These men had to answer it, in stone, in real time, without the ability to start over. What they were about to do was either going to save the pyramid or confirm its destruction. They had no way to know which. They had only the decision itself, and the courage or the desperation or the sheer refusal to accept failure, to make it. Imagine walking into a pyramid, not as a tourist, with electric lights and handrails and the soft murmur of other visitors around you. Walk into it the way an Egyptian overseer would have walked into it 4,600 years ago. With oil lamp in hand, the flame small and yellow and easily extinguished by a wrong movement of air. With the weight of millions of tons of stone pressing down from above. With the sound of the desert outside disappearing behind you and the silence of enclosed rock replacing it. A silence that is not peaceful but geological. The silence of something enormous and permanent and completely indifferent to the fact that you are inside it. The passage descends steeply. The ceiling is close. The walls on either side are cut limestone blocks, each one fitted against the next with precision that should be reassuring. And in this moment is not reassuring at all. You are not here for ceremony. You are not here to practice rituals or measure dimensions or oversee the placement of the next course of stone. You are here because someone told you something was wrong. And now, lamp rays, moving deeper into the body of the pyramid, you are about to see it for yourself. This is the moment the bent pyramid's construction crisis becomes real. Not as an abstraction, not as a geological process operating invisibly in the shale far beneath your feet, but as a visible, undeniable, physically present fact inscribed in the walls and ceiling of the chambers and passages that you and your workers built with your own hands, and that the pyramid is now, quietly and methodically, attempting to destroy. The evidence left behind inside the bent pyramid is among the most extraordinary archaeological records of structural distress in the ancient world. It is not hypothetical. It is not inferred. It is there in the stone, exactly where the crisis left it, waiting for modern engineers and archaeologists to read it the way a physician reads symptoms, each one telling part of the story, and the story telling the whole diagnosis. Start with the chambers. The bent pyramid contains two primary internal chambers, each built using the corbelled vault technique, described in the previous chapter. Those narrow, tapering, inverted V-shaped spaces where successive courses of stone project inward above the open room below, reducing the span incrementally until the two sides meet at the top. The lower chamber sits deep within the body of the pyramid, reached by the descending north corridor. The upper chamber sits higher in the structure, reached by the west corridor that enters the pyramid at a point roughly a third of the way up its height. Both of these chambers were built with extraordinary care. The corbelling is precise. The stone is well cut. In another pyramid, on another foundation, these chambers might have stood without incident for 10,000 years. But inside the lower chamber of the bent pyramid, something happened to the corbelled walls that reveals the full nature of the crisis with terrible clarity. The walls lean, not dramatically, not in a way that a casual visitor, had casual visitors been permitted, would necessarily notice immediately, but measurably, demonstrably, under the sustained pressure of the settling foundation and the accumulating weight of the stone above, the walls of the lower chamber had displaced inward, the corbelled courses pushing toward each other with a force that the original design did not anticipate, and that the ground beneath the pyramid created by shifting, settling, compressing, doing precisely what clay-bearing shale does when you stack an enormous pyramid on top of it. The walls are moving toward each other, not quickly, not all at once, in the slow, inexorable language of structural failure under enormous load. The walls of that chamber are closing. And as they close, the joints between the corbelled courses, the carefully fitted surfaces where one stone rests on the next, are opening, or cracking, or doing the thing that joints between stones do when the stones themselves are being displaced, failing to maintain the integrity they were laid to preserve. Now add to this the evidence of the repairs. Inside the passages and chambers of the bent pyramid, archaeologists have found extensive traces of gypsum plaster applied to the walls in ways that go far beyond standard finishing. Plaster was a common material in Egyptian construction, used for smoothing, for decoration, for the application of painted text and imagery. But the plaster found in certain sections of the bent pyramid's interior is not decorative. It is structural. It is packed into gaps and fissures in stone with the focused urgency of someone trying to stop something from getting worse. These are repairs. Ancient, desperate, applied in the moment repairs. Someone found cracks. Someone mixed plaster. Someone pressed that plaster into cracks in the walls of a chamber that was supposed to be the eternal resting place of a god king. Try to hold the stone together with material that cures to roughly the hardness of dry clay. This is one of the most quietly heartbreaking images in all of ancient engineering. Not because the plaster was inadequate, though it was but because of what it tells us about the state of mind of the people applying it. They knew the cracks were there. They knew, at some level, that cracks inside a chamber buried within hundreds of thousands of tons of settling stone were not a cosmetic problem. And they plastered them anyway. Because what else do you do when the wall in front of you is cracking, and the pyramid above you is half-built, and stopping is not a conceivable option? You fill the crack. You move on. You hope. And then there are the cedar logs. This is the detail that, more than any other physical evidence, communicates the raw immediacy of the crisis. Cedar from Lebanon, expensive, imported, worked with care, placed inside the passages and chambers of the bent pyramid, not as decoration, not as part of any funerary or religious function that Egyptologists can identify, but as props. Physical, structural props, wedged into passages to prevent the walls from continuing to close. Placed in positions that make sense only if the person placing them was looking at a passage that was narrowing and trying to stop it from narrowing further. You do not import cedar from Lebanon to prop up a pyramid. That is fine. You import cedar from Lebanon at considerable cost and effort, because the passages inside your pyramid are literally closing under the weight of the stone above them, and you need to hold them open so that people can still move through them, so that the builders can still access the interior, so that eventually the rituals of the burial can still take place in chambers that still exist as chambers rather than as collapsed voids inside a solid mass of failed stone. The logs of the crisis made tangible. They are the emergency measure, the ancient equivalent of the temporary shoring a modern construction engineer throws up when a wall starts to move, and the first priority is simply stopping it from moving further before you can figure out what to do next. But here is what makes the cedar logs particularly significant beyond their function. They speak to timing. They were placed there during the construction, during the period when the pyramid was still being built above them, which means the crisis was not discovered after the pyramid was finished and the builders had moved on. It was discovered mid-construction, while the structure was still rising, while the foundation was still receiving new weight with every layer of stone added above, while the very process of building the monument was simultaneously worsening the conditions that were tearing it apart from within. The pyramid was under construction above ground and under assault below ground at the same time. This is the full horror of the situation. You cannot simply stop building while you fix the interior, because stopping the external construction does not stop the geological process occurring in the foundation. The shale beneath continues to compress regardless of whether the workers above are adding new stone. The damage continues to accumulate, and every day that the crisis persists unresolved is a day in which the window for any effective response is potentially narrowing. But neither can you simply keep building as if nothing is happening, because what is happening inside the pyramid is a direct function of the forces that building is creating. Every new layer of stone added to the rising exterior increases the load on the foundation, increases the pressure on the internal chambers, accelerates the very settling that is causing the walls to lean and the passages to close. You are in a situation where building is causing the damage, and stopping the building does not stop the damage. And you have already committed enormous resources and years of labor to a structure that is now fighting its own existence. Now add the dimension that no modern engineer has ever had to face in quite this form. The man for whom this pyramid is being built is not an abstract client. He is not a corporation or a government agency whose displeasure carries professional consequences. He is a God King. He is a living deity whose eternal passage into the afterlife depends on the correct completion of this monument. The theological stakes are not a metaphor. In the worldview of everyone involved in this project, the workers, the overseers, the architects, the administrators, the Pharaoh himself, the pyramid is not a building. It is a mechanism of cosmic consequence. And a pyramid that fails is not merely a construction disaster. It is a rupture in the order of the universe. Think about the man who had to report this crisis. Whoever he was, an overseer, a chief architect, a site administrator. He had to travel to wherever Sneferu was. He had to arrange an audience. He had to stand in the presence of man who was, in the understanding of that culture, the son of Ra, the embodiment of divine order on earth, the fulcrum of the cosmos. And he had to say, with whatever words he chose, something that translated to this: the pyramid is cracking. The foundation is moving. The chambers are failing. and we do not know with certainty how to stop it. We have no record of that conversation. No inscription, no papyrus, no relief carving captures the moment when a pharaoh's monument was reported to be failing him. The silence of the historical record on this specific human, terrifying exchange is absolute. But the consequences of the conversation are written in stone, because something changed at Dahshur, something that left a permanent mark on the exterior of the pyramid, visible from miles away, visible from the air, visible to every person who has stood in this desert in the 4,600 years since the decision was made. The angle changed. At 147 feet above the desert floor, at the precise elevation where crisis had reached a point that demanded a response that plastering and propping and hoping could no longer provide, the builders shifted their angle from 54 degrees to 43 degrees, 11 degrees, a number that sounds small until you hold it against the physical scale of the structure involved and the engineering consequences of the choice. 11 degrees shallower, 11 degrees less deep. And what those 11 degrees meant, in terms of load reduction, weight distribution, the forces acting on the foundation and the chambers and the failing walls of that lower vault, was a difference between a pyramid that would eventually and totally collapse and one that would stand. Though nobody knew that yet, because the decision to change the angle was not made with confidence. It was made under pressure mid-crisis by engineers working with the knowledge they had, the materials available to them, the time they did not have, and the weight, the enormous, sacred, unmovable weight of a pharaoh's eternity pressing down on every calculation. They were not certain it would work. They could not be. They only knew that continuing at 54 degrees was certainty of a different kind, a certainty they could not accept. And so they made the bend, 11 degrees, a decision carved into the exterior of the pyramid in a moment of desperation that became, over the next 4,600 years, the most recognizable feature, the most unusual monument in all of Egypt. But the change in angle, as radical as it was only part of what needed to happen, because changing the slope of the exterior addressed the forces acting on the foundation from above. It reduced the load. It slowed the settling. It gave the ground a chance, perhaps, to stabilize under a weight that was no longer increasing at the same catastrophic rate. What it did not do was address what was already broken inside. The chambers, the corbelled walls, the passages that cedar logs were holding open, the cracks that plaster could not seal, the settling that was continuing its quiet work in the stone and the shale regardless of what was happening on the surface above. To address those problems, the builders needed something else entirely, something they had never built before, something that existed nowhere in the architectural tradition they had inherited, a solution that would require them to think about the distribution of force inside a stone structure in a way that no Egyptian engineer had ever been forced to think about it before. They were going to have to reinvent how a pyramid worked from the inside. And the solution they found, the specific, elegant, desperate solution they applied to the failing interior of the bent pyramid, was so effective, so structurally sophisticated, that the engineers who built the monuments that came after would use versions of it for the rest of the Old Kingdom. The crisis did not just produce a bent pyramid. It produced a new way of thinking about stone. And that thinking was about to save everything. Here is something that sounds simple and is not simple at all. Change a pyramid in the middle of building it. Read that sentence again. Let the full weight of it settle. Because what it actually means, when you strip away the abstraction and replace it with physical reality, is this. Take a structure composed of millions of individual stones, each one weighing between 2 and 15 tons, each one placed with geometric precision relative to every stone around it, each one part of an interlocking system of load distribution that was designed at a specific angle for a specific total height, for a specific total mass, and then change the angle while the structure is still being built, without removing what has already been placed, without the ability to start over, without stopping the geological failure that is continuing in the foundation below, or the structural distress that is continuing the chambers within, while you figure out how to do this. Change the angle, mid-construction, in stone. This is what was decided at Dahshur. And the first thing that must be said about this decision, before the engineering, before the mathematics, before the structural logic, is that it required a quality that engineering textbooks do not usually discuss. It required a willingness to accept that the original plan was wrong, not slightly miscalculated, not capable of small adjustment, wrong, fundamentally, demonstrably, dangerously wrong, and to accept that and to commit publicly to changing it. In a culture where the pyramid was a divine commission, where the pharaoh was a god, where any deviation from the sacred original intention carried implications that extended from the purely practical into the cosmological, this acceptance was itself an act of courage that history has never adequately recognized. No inscription celebrates the man or men who made this call. No relief carving in any temple records a meeting where the decision was finalized. Egyptian culture was not inclined to memorialize moments of institutional crisis or royal engineering failure. What happened at Dahshur was addressed in stone, not in words. The pyramid itself became the record. The bend became the monument to the decision. And the decision itself, whoever made it, however it was framed, whatever words were used in whatever conversation with Sneferu, that decision is present in the structure forever, visible from miles away, permanent as the limestone it was carved into. Let us now follow it into the engineering. At 147 feet of elevation, the building of the upper section of the bent pyramid begins at 43 degrees. The lower section, the roughly 60% of the pyramid's total mass that had already been laid before the crisis forced a change, remains at 54 degrees. It cannot be removed. It cannot be altered. It is already there, already locked into the foundation, already part of the settled and settling geological reality beneath. The builders accept it completely and build from it. What 43 degrees does, relative to 54 degrees, is change the geometry of the structure's upper mass in a way that has immediate and dramatic consequences for the forces bearing down on the foundation and the chambers below. Consider the shape produced by the two angles together. At 54 degrees, the pyramid would have continued rising steeply, concentrating its apex at a point directly above the center of its base at a height of roughly 128 meters. The sides would have swept upward at an aggressive, narrow angle. The upper mass would have been tall. And tall, at the steepness of 54 degrees, means heavy in a very specific and very dangerous way. The weight of the upper mass pressing almost vertically downward to the structure, channeled by the geometry of steep sides into a crushing force aimed directly at the center of the foundation. At 43 degrees, everything changes. The shallower angle means the upper section of the pyramid spreads outward more than it rises. Each new course of stone, instead of stacking almost directly above the one below it, steps slightly further out toward the existing 54-degree sides. The mass of the upper section is distributed more laterally, spread over a wider footprint rather than piled vertically above a narrow center point. The force vectors, the directions in which the weight of the upper stone is pressing, shift. They press outward toward the sides more and downward toward the center less. This matters enormously to the foundation. What the foundation at Dahshur could not tolerate was the specific pattern of vertical loading that 54 degrees was imposing. The way it concentrated enormous downward pressure at the center, where the chambers were, where the foundation was most compromised, where the shale beneath had already begun to compress and shift under the assault. 43 degrees did not eliminate the load on the foundation, but it redistributed it, spread it, gave the unstable ground below a different, more manageable pattern of forces to absorb. Think of it this way. If you place all your weight on the very center of a thin sheet of ice, it cracks at the center. If you spread your weight across the full surface of that same ice, it holds. The ice has not changed. The weight has not changed. Only its distribution has changed. And distribution, as the builders of the bent pyramid were discovering in the most consequential way possible, is a fundamental problem of structural engineering. The external angle change was the first response to the crisis. It was visible. It was dramatic. It permanently altered the silhouette of the pyramid against the Egyptian sky. But it was not sufficient on its own, because the damage was already inside. And changing what was happening on the exterior surface of a pyramid does not immediately or automatically repair what has already happened to its interior chambers. The lower chamber's walls had displaced. The passages had closed. The corbelled courses had shifted under pressure that was ongoing, and that a change in exterior angle, however radical, could not retroactively undo. What the builders needed to do inside the pyramid required a different kind of thinking. Not the large-scale geometry of the exterior, but the intimate, detailed, almost surgical thinking of structural intervention in spaces already under assault. And here's where the story becomes something remarkable. The corbelled vault, the technique used in both chambers of the bent pyramid, is, in its original conception, a passive structure. It distributes load by geometry alone. Each overhanging course of stone transfers its weight to the course below and outward toward the walls, and from the walls into the surrounding stone mass of the pyramid. It works because the geometry of the corbel means the load never has to be borne by any single stone spanning an open gap. There is no tension member, no keystone. Every stone is in compression, pressing down onto the stone below it, and compression is what stone handles best. But passive structures have limits. They work within a range of conditions. Step outside that range, put them under asymmetric loading, subject them to differential settlement in the foundation, surround them with a pyramid that is compressing unevenly because the ground beneath it is not uniform, and the corbelled vault begins to fail in ways its designers did not account for. What the builders of the bent pyramid did next, what they did to the failing interior, while simultaneously changing the exterior angle above, was to transform the passive corbelled vault from a structure that simply existed in the space around it into something more active, more interventionist, something that reached outward from the chamber walls and engaged with the surrounding stone mass in a new way. The key insight was this. The corbelled chambers were failing because the force arriving at their walls from the settling foundation and the pressing stone above was arriving unevenly. One side of a chamber receiving more pressure than the other causes the walls to displace asymmetrically, to lean, and leaning in a corbelled vault is the beginning of collapse because the whole geometry of the structure depends on the two approaching sides being in symmetric relationship. Disturb that symmetry enough, and the corbelled courses no longer distribute load outward into the walls. They begin to press inward toward each other, which is structurally catastrophic. The response was to pack the space around the chambers more densely and more deliberately, to add stone, carefully cut, carefully placed, in ways that reinforced the walls of the chambers from outside, increasing their resistance to the asymmetric forces pushing against them. To use gypsum mortar not just as a surface treatment, but as a genuine structural binder in the critical joints where displacement was occurring. To, in effect, increase the effective thickness and stability of the chamber walls by treating the surrounding stone of the pyramid's body as an active structural partner rather than a passive surrounding mass. This sounds technical. In the raw fact of it, it was builders in an oil lamp-lit chamber underground, inside a failing pyramid, manually reinforcing walls that were moving toward them, packing stone and mortar into spaces with their hands, working against a process that was larger than them and had been building for months. The cedar props remained, were supplemented, possibly, were repositioned as the work of reinforcement proceeded. They held the passages open while the work was done around them. And when the work was finished, when the reinforcement was as complete as the builders could make it, when the new stone packing was in place, when the mortar had set, the passages were still open. The chambers still existed as chambers. The corbelled vaults, though displaced from their original geometry, had not collapsed. The intervention had worked. Not perfectly, not elegantly, not in the way that the original design had intended any of this to work, but it had worked. Now, go back to the exterior. The upper section of the pyramid rises at 43 degrees from the 147-foot transition line. And it rises with something else the lower section does not have, a significantly different approach to internal space. The upper chamber of the bent pyramid, the one reached by the west corridor, the one sitting higher in the structure, contains corbelling on a scale and to a quality that exceeds almost anything in the pyramid building tradition up to this point. The corbelled vault of the upper chamber rises approximately 17 meters from floor to apex. 17 meters. Nearly 6 stories of carefully graduated, perfectly fitted limestone corbelling. Each course projecting inward by just the right distance to maintain structural integrity while maximizing the height of the interior space. It is astonishing, standing inside it, and visitors today can still enter this pyramid, one of the very few in Egypt that allows interior access. You crane your neck upward, and the corbelled walls rise above you in a kind of stone tunnel that narrows as it ascends, the courses growing closer together until they meet far overhead in a narrow strip of stone. The geometry is exact, the masonry is expert, and the sophistication of the engineering that produced it reflects, in concentrated form, everything that had been learned from the crisis occurring simultaneously in the chamber below. The builders of the upper section were building with knowledge they did not have when the lower section was designed. They knew, now, what happened when a corbelled chamber was subjected to asymmetric loading from a settling foundation. They knew because they were living inside the consequences of it in the chambers below their feet. And they applied that knowledge to every decision made in the upper section. The angle of the corbelled projections, the thickness of the walls, the relationship between the chamber height and the surrounding stone mass, the careful, deliberate reinforcement of every structural joint. The upper chamber of the bent pyramid is not just a room. It is a lesson, encoded in limestone, about what happens when engineering knowledge is tested to destruction and the survivors build again with everything they have learned. But now consider what was sacrificed. The pyramid that was designed, the 54-degree monument that would have risen to a height of roughly 128 meters, clean-sided and geometrically perfect, the distilled expression of Egyptian cosmological ambition. That pyramid does not exist. It was never built. It died in the shifting shale beneath Dahshur. What was built instead is something that has no precedent in Egyptian architecture, no parallel in the entire 3,000-year history of the civilization that produced it. A pyramid with two angles. A pyramid that bends. And for a civilization in which the pyramid's meaning was inseparable from its perfection, this matters enormously. The pyramid was supposed to be the eternal, the unchanging, the geometric absolute. A pyramid with a kink in its profile at 147 feet is a pyramid that carries a memory of its own crisis permanently on its face. It cannot be smoothed over. It cannot be explained away. Every person who looks at the bent pyramid looks at a monument that failed to be what it was meant to be, and that survived anyway. And that stands today precisely because the people building it refused to let the failure become total. There is a question that Egyptian theologians of the Old Kingdom must have grappled with, though no text survives to tell us how they resolved it. Was this pyramid still valid? Was its divine function, the passage of Sneferu's soul through death into eternal existence, still intact? Was a bent pyramid acceptable to Ra, to Osiris, to the cosmic order that required the pyramid's perfection as its physical expression? We cannot know the answer they arrived at. We can only observe the consequence. Sneferu was not buried in the bent pyramid. His burial, his actual interment, the culmination of everything a pyramid's construction was ultimately for, took place in the Red Pyramid, a third monument, built at Dahshur, begun perhaps while the crisis at the bent pyramid was still being resolved, and built entirely at 43 degrees from the foundation to the apex. Clean-sided, geometrically consistent, no bend, no compromise in the exterior profile. The angle that saved the bent pyramid became the angle of the Red Pyramid from the start. Sneferu's builders took the desperate, crisis-born solution of 43 degrees and chose it deliberately for their next project. Not because they had to, because they had learned, in the most consequential way possible, that 43 degrees worked, that it was survivable, that a pyramid built at this angle, on a properly evaluated foundation, with the internal engineering knowledge now purchased at such tremendous cost, would stand. They took the lesson of the crisis and made it the foundation of the next achievement. And the Red Pyramid stands, today, fully intact, the third largest pyramid ever built in Egypt, the first true, smooth-sided pyramid ever completed and used for its intended purpose. The monument that proved the bent pyramid's crisis was not the end of Egyptian ambition. It was the education of it. But the Red Pyramid was not the end. It was not even the most significant consequence of what happened at Dahshur, because the knowledge carried out the bent pyramid's crisis, the understanding of foundation behavior, of load distribution, of corbelled vault reinforcement, of the relationship between exterior angle and interior structural health, did not stop at the Red Pyramid. It traveled north, to a plateau above the Nile, 45 miles from Dahshur, to a site called Giza, where a pharaoh named Khufu was about to use everything his father Sneferu had learned, paid for in crisis in cedar and gypsum plaster, and the bend visible on the horizon at Dahshur, to build something that would outlast every monument in the history of the world. The bent pyramid's greatest achievement was not its own survival. Its greatest achievement was what its survival made possible. Stand at the base of the Great Pyramid of Giza and look up. Most people, when they do this for the first time, stop thinking entirely. The scale overwhelms the analytical mind and replaces it with something more primitive, a wordless recognition that what you are standing next to is not a building in any sense that the word normally conveys. It is a geological event that human beings caused, a mountain that was designed, the kind of thing that makes you understand, in your body rather than your brain, why the ancient world considered this one of its 7 wonders, and why the modern world, having lost 6 of those 7 times, has kept this one on the list not as a courtesy to antiquity, but as a straightforward acknowledgement of what it is. The Great Pyramid of Khufu, built roughly 4,580 years ago, rising to an original height of approximately 146 meters. Every centimeter of it filled with precision-cut limestone, with internal passages that descend and ascend through its body with geometric exactitude, with chambers that sit in the heart of this enormous mass and have not collapsed in 4.5 millennia. The largest pyramid ever built, the most precisely constructed large structure in the ancient world, the monument against which all other monuments are measured, and against which most of them quietly lose. Khufu was Sneferu's son. He grew up in a kingdom being reshaped by stone. He watched, as a prince, as his father's construction programs transformed the desert south of Memphis into a sequence of monuments that announced Egyptian ambition to the sky. He absorbed everything: the organizational systems, the quarrying techniques, the logistics of feeding, and housing a construction workforce of tens of thousands, the theological framework that made the pyramid not just a building, but a cosmic necessity. And he absorbed something else. Something that came to him not through ambition or theology or administrative genius, but through the specific hard-won, pain-purchased knowledge that his father's builders had extracted from the crisis at Dahshur. He inherited the lessons, and the first and most fundamental of those lessons was about the ground. Look at where Khufu built. The Giza Plateau is a limestone massif, a natural elevation of solid rock rising above the western edge of the Nile Valley, not desert surface. Not alluvial deposits, not clay-bearing shale hidden beneath a deceptively solid-looking floor. Bedrock, the kind of foundation that does not compress under load, the kind that does not shift under sustained pressure, the kind that once leveled, and Khufu's builders leveled it with extraordinary precision, creating a foundation surface that deviates from perfectly flat by less than 2 centimeters across its entire enormous area. Stays level. This choice was not random. The Giza Plateau had been visible and available for as long as Egyptian civilization had been building pyramids. Djoser's builders could have gone to Giza. They did not. The builders who started at Mitam could have gone to Giza. They did not. Sneferu himself, choosing Dahshur for the bent pyramid, could have evaluated Giza. Whether he did and rejected it, or whether the imperative of demonstrating dynastic presence in the Dahshur region drove the choice, we cannot say with certainty. What we can say is that by the time Khufu's planners were choosing their site, the importance of foundation stability had been written into the institutional memory of Egyptian engineering in letters of cracked limestone and displaced corbelled walls and cedar props holding open-closing passages in the dark. Giza was chosen because of what Dahshur had taught. The bedrock foundation of the Great Pyramid is its first and most invisible inheritance from a crisis of the bent pyramid, and it is arguably the most important. Because everything that was built on top of it, all the precision, all the internal engineering, all the magnificent internal spaces, depends on the foundation not moving. And the foundation does not move because it is solid limestone all the way down, chosen deliberately, chosen knowingly, chosen by builders who understood now, in a way their predecessors at Dahshur had not, exactly what happened when the ground beneath the pyramid was wrong. Now go inside. Descend into the body of the Great Pyramid through its entrance on the north face, and follow the passages as they lead you toward the heart of the monument. You will pass through spaces that no person's fully understood. The subterranean chamber carved into the bedrock beneath the pyramid, the ascending passage that rises at a steep angle for the pyramid's body, the so-called Queen's Chamber that sits in the middle of the structure, and eventually you arrive at the most extraordinary interior space in the entire history of ancient architecture, the Grand Gallery. It is 47 meters long and 8.5 meters high. It runs at an angle of approximately 26 degrees through the body of the pyramid, ascending from the intersection of the horizontal passage to the entrance of the King's Chamber above. Its walls are smooth limestone. Its floor is lined with kind of track or groove whose purpose scholars still debate. And its ceiling is a corbelled vault. A corbelled vault. The same technique used in the chambers of the bent pyramid. The same structural principle. Successive courses of stone projecting inward above the open space below, distributing the weight of the pyramid above outward into the walls rather than concentrating it as a crushing load on any single span. But here, in the Grand Gallery, the technique has been taken to a level of refinement and confidence that makes the corbelling in the bent pyramid look like what it was, an earlier iteration of the idea, built by engineers who were still discovering its limits. The Grand Gallery's corbelling rises through 7 courses on each side, each course projecting inward by just the right distance, the geometry maintained with precision that produces not just a structurally sound space, but a visually extraordinary one. Standing in the Grand Gallery for the first time, you look up into a narrowing tunnel of stone that rises above you like the nave of a cathedral, and the craftsmanship is so assured, so settled, so utterly free of the desperate improvisation that characterize the bent pyramid's interior interventions, that you understand immediately you are looking at the product of mature knowledge. This is what it looks like when the lessons have been fully absorbed, when the engineers building the vault are not fighting structural failure while they work, but drawing on the memory of having fought it, and of having won, and of having understood precisely why they won and what they would do differently the next time. The Grand Gallery is what the bent pyramid's upper chamber looks like after a generation of refinement. The upper chamber of the bent pyramid was the first expression of corbelled vault engineering pushed to its limits under extreme duress. The Grand Gallery is the same thinking, free of crisis, executed with total confidence at a scale and quality that has never been matched in 4,500 years of subsequent human building. But the Grand Gallery is not the end of the inheritance. At the top of the Grand Gallery, the King's Chamber waits. The King's Chamber of the Great Pyramid is built not of limestone, but of Aswan granite. A stone so hard that the copper chisels of the Old Kingdom could barely scratch it, worked into blocks so large and so precisely fitted that a piece of paper cannot be slid between them. The chamber is a rectangle of severe simplicity. No decoration, no inscription, just the precision of the stone itself and the silence of a room that has sat in the center of the most famous building on earth for 4,500 years. And above the ceiling of the King's Chamber, there is something that no visitor can see, but that every structural engineer who has studied the Great Pyramid regards with deep respect. 5 compartments. 5 low, narrow spaces stacked one above the other above the ceiling of the King's Chamber, each separated from the next by enormous granite beams. The spaces are sometimes called relieving chambers, though modern engineers prefer the term construction chambers, because the debate about their precise structural function is genuinely ongoing. But what they accomplish, whatever the designers intended, is this. The weight of the pyramid above the King's Chamber is not borne by the ceiling of the chamber directly. It is intercepted by this sequence of compartments and massive granite beams, which distribute the load outward and away from the chamber itself, carrying the weight toward the walls of the pyramid's body and from there down to the bedrock foundation. The pressure that would otherwise crush the ceiling of the King's Chamber is redirected, spread, made manageable by a layered system of load distribution that sits invisibly above the room where the king was meant to rest for eternity. Load distribution. The same fundamental principle that the corbelled vault embodies. The same fundamental problem. How do you put a human-scale void inside a mountain-scale solid and prevent the solid from destroying the void? That the builders of the bent pyramid's internal chambers were solving with cedar logs and gypsum plaster under conditions of active structural failure. The 5 compartments above the King's Chamber are the bent pyramid's crisis translated into deliberate, pre-planned, exquisitely executed architectural language. They are what happens when the question of load distribution, learned under emergency conditions at Dahshur, becomes the basis of intentional design at Giza. They are, in the most direct sense available to us, Sneferu's gift to his son. Now step back from the engineering. Step back from the specific techniques and the structural logic and the angle mathematics and the corbelled vault geometry. Step back and look at the full sweep of what Sneferu's reign produced. He arrived at the throne of Egypt at a moment when the pyramid tradition was still young. The step pyramid of Djoser was approximately 2 generations old. The idea of a true pyramid, smooth-sided, geometrically absolute, was a theological aspiration that had not yet been tested against the physical reality of actually building one. The gap between the vision and the execution was full of unknowns. Sneferu's reign crossed that gap, and crossing it cost him. The Midim conversion, whatever its ultimate fate, was an experiment in turning theory into practice. The bent pyramid was that experiment's most consequential chapter, a crisis that pushed the entire pyramid-building enterprise to the edge of catastrophic failure and forced it to find solutions it would never otherwise have looked for. The red pyramid was a proof that the solutions worked, and it served simultaneously as Sneferu's actual burial monument, the first successful true pyramid, and the prototype for the next and greatest achievement in the tradition. 3 pyramids, possibly 4, more stone moved in a single reign than in any other in the history of Egypt. And not one of those pyramids was built without teaching something. Not one was built without expanding the knowledge base of an engineering tradition that was, in Sneferu's time, working almost entirely from first principles. The total volume of stone in Sneferu's confirmed pyramids, the Midim monument, the bent pyramid, and the red pyramid, is estimated at approximately 3.5 million cubic meters. Khufu's Great Pyramid contains approximately 2.5 million cubic meters. Sneferu's entire program outweighs his son's masterpiece by a significant margin, and yet the name most people know is Khufu. The monument most people photograph is the Great Pyramid. The achievement most people celebrate is Giza. This is a peculiar justice of history. The person who breaks the ground, who makes the mistakes, who absorbs a crisis, who pays the price of figuring things out for the first time, is rarely the person the world remembers. It is the next generation, the one that inherits the lessons without inheriting the chaos, that gets to build a thing that everyone celebrates. Khufu stood on his father's shoulders, literally and structurally. But here's the thing about Sneferu's legacy that history has been quietly reassessing over the last century of Egyptological scholarship. He was not a failure. He was not a pharaoh who built badly and got lucky. He was the most consequential builder in the history of pyramid construction, not because his monument is the most famous, but because his building program was a crucible in which the knowledge required for the most famous monuments was forged. The bent pyramid in particular is not a monument to failure. It is a monument to learning. It is a building that carries its education on its face. Every other pyramid in Egypt presents a smooth, uniform, completed surface, a finished argument about permanence and perfection that conceals whatever difficulty went into its making. The bent pyramid is the only one that shows the difficulty, the only one that wears the evidence of crisis, of decision, of response, of recovery, permanently in its exterior profile for anyone with eyes to read. At 147 feet above the desert floor, the angle changes and everything changes with it. That bend is not a flaw. It is a record. The most complete, most permanent, most legible record that survives a moment when human builders encountered the limits of what they knew, were forced to learn something new, and learned it well enough that what they learned outlasted them by thousands of years. The bent pyramid has stood for 4,600 years. It has outlasted every civilization that has risen and fallen in the territory around it since the day the last stone was placed. It has outlasted the Egyptian language in which its builders thought and spoke and argued and solved. It has outlasted the theological system that gave it meaning, the political system that funded it, the administrative machinery that organized it, and the individual human beings, whose names we do not know, whose faces we cannot see, whose specific moment of crisis and insight and decision are accessible to us only through the physical record they left behind. Who built it? It still bends. The angle still changes at 147 feet. The lower section still rises at 54 degrees, the upper section at 43. The transition line is still as visible from a distance as it was on the day it was made. The pyramid that was supposed to be perfect is still imperfect, in exactly the way it became imperfect when the crisis happened, and it is still standing, which means the imperfection is the thing that made it stand. There is something in this that exceeds engineering. Something that touches a deeper question about what monuments are for and what they ultimately preserve. We build monuments to project permanence. To say this happened, this mattered, this person or this achievement or this civilization should not be forgotten. The smooth pyramid says, we were perfect. We were eternal. We were without flaw or doubt or difficulty. We were the divine-made stone. The bent pyramid says something else, something more difficult and more honest and perhaps more enduring. It says we built something. The ground moved beneath us and the walls cracked in the dark and the passages closed and we did not know if we could save it. And we changed what we were building in the middle of building it, in stone, with no guarantee it would work. And it worked. And here we are, still here, still standing. After everything, that is not a lesser monument. That is a greater one. There is a kind of knowledge that can only be purchased by crisis, not the knowledge in books or in the instructions passed from teacher to student or in the accumulated theory of a technical tradition. A different kind, the kind that lives in the body of a system that has been tested past its limits and survived, the kind that a civilization carries forward not in its words but in the choices it makes afterward, in the foundations it chooses more carefully, in the angles it selects with more humility, in the internal spaces it designs with a memory of what happens when internal spaces fail. The bent pyramid contains this knowledge. It is a physical record of the moment Egyptian engineering crossed from aspiration into understanding. Before the crisis at Dahshur, the pyramid tradition was built on ambition, theology, and the accumulated intuition of craftsmen working from experience they could not fully articulate. After the crisis at Dahshur, it was built on something harder and more reliable, evidence. The evidence of what happens when the foundation moves. The evidence of what happens when the angle is too steep. The evidence of what happens when the weight above a corbelled chamber is distributed unevenly and the walls begin, slowly and measurably, to lean toward each other. And the evidence, paid for at enormous cost, in a monument that would spend every century of its existence wearing the proof of its own crisis on its exterior, of what happens when you respond to that knowledge rather than refusing it, when you change the angle, when you reinforce the walls, when you make the radical, difficult, unprecedented decision that the original plan was wrong and that surviving matters more than appearing to have been right all along. For 1,600 years later, the bent pyramid still teaches this. To every archaeologist who has mapped its interior, to every engineer who has analyzed its structural behavior, to every person who has stood in the desert at Dahshur, looked up at that changed angle, and asked the question that the pyramid has been waiting to answer since the day the decision was made. What happened? What happened was this. A civilization building at the edge of its knowledge found the edge, and instead of falling off it, it stepped back, looked at where the edge was, and built the next thing further from it, more carefully, more wisely, with the full benefit of everything the near fall had taught. The Great Pyramid of Giza, the structure that has defined human ambition in stone for 4,500 years, the building that has outlasted every subsequent civilization's best attempt to surpass it, the monument that still, today, generates wonder in every person who stands at its base and looks up, stands on bedrock. Chosen deliberately, it stands with corbelled vaults perfected through crisis. It stands with load distribution systems above its innermost chamber that reflect a mature, sophisticated understanding of how to protect a void inside an enormous solid from the forces trying to fill it. It stands because of what broke at Dahshur. It stands because of the cedar props wedged into closing passages in the dark, because of the gypsum plaster pressed into cracks by hands we will never identify, because of the decision made at 147 feet that bent a pyramid into a shape no pyramid was supposed to have, and in bending it, saved it, and in saving it, preserved a knowledge that would build the greatest monument in human history 45 miles to the north. This is a hidden architecture of civilization, not the famous monuments, the celebrated moments, the achievements that fill the history books and the tourist photographs, but the crises behind them, the failures that were almost total, the decisions made under pressure in the dark by people who did not know if what they were choosing would work, who made the choice anyway, who built on the knowledge the crisis had generated, and who left, in stone and ruin, in the bend of an angle on a desert horizon, the record of what it actually cost to advance a human project by one step. We celebrate the Great Pyramid. We should also celebrate the bent pyramid. Not because it is beautiful, though it is, in its strange and asymmetric way, genuinely beautiful. Not because it is perfect. It is famously, permanently, visibly imperfect. But because of what it is honest about. Because it is the only pyramid on earth that shows you what pyramid building actually involved. Not the divine commission completed without difficulty. Not the god kings will express seamlessly in stone, but the human reality of attempting something at the absolute limit of what was known, encountering the consequences of that limit, and surviving them with the willingness to change. The bend at 147 feet is not a monument to failure. It is a monument to the moment someone looked at a failing pyramid and chose, against every precedent, against every pressure, against every theological imperative that demanded the original plan be honored without deviation, chose to change the plan. And in making that choice, in that moment, in that desert, with cracking walls in the dark below and an unfinished monument rising into the Egyptian sky above, they did something that every engineer, every architect, every builder of every kind and every civilization has followed has had to do at least once, in some form, under some pressure, with some version of the same fear. They bent, and the bending held.